Durgaram, sir, shall we start?
Yes, yes. We can start now.
I think two more speakers to join, sir. So meanwhile, we will start, sir.
Mr. Nandi is also joined sometime back.
Yes, sir. Yeah. So good afternoon, all. On behalf of CA, it is my pleasure to welcome Session Chairman Mr. R. Durgaram, speakers and as participant to this 18th Greentech Cementech program. In this, we are going to cover the topic on best practices and waste and efficiency improvement opportunities being adapted and going to be adapted in waste heat recovery system. I'm just going to give some moment to give a brief for Mr. our session chairman Durgaram. Currently, he's working as a head CPP JK Cement Muddapur, having a total experience of around 20 years, skilled in thermal power plant, waste heat power, project engineering, commissioning, operation and maintenance. Also, he holding a BOA and energy auditor certification. I request Durgaram sir to take up this session and lead. Thank you, sir. Over to Mr. Durgaram.
Thank you, Mr. Marimuthu. Very good afternoon and warm welcome to all CIE executives, delegates, and participants. My sincere thanks and privilege to CIE as well as our JK management for this given opportunity. About the session, we are going to interact with the experts who are having a vast experience on WHRS adapted best practices and adapted latest improvements in their systems. Currently, we all are very much aware about the fuel crisis scenario, like fuel cost, as well as the supply side issues. Now, better time we go with the WHRS system, which is very much essential part in the industries. About the advantages, we can say we can reduce the fuel cost and specific energy consumption in the plant significantly by the way of adopting WHRS systems. Moreover, we can mitigate the emission of greenhouse gases which are affecting the environment adversely. Also, we can generate the required power from the emitting huge quantity of waste heat only by the method of waste heat recovery systems. Only some 2-3 areas we have to take care while planning for the WHR system, like all waste heat recovery boilers have huge heat surface area and huge footprinting area. So those things we have to take care before designing as well as the construction durations. While talking about the operation issues, we can say that soot deposition on the tube sites will be very higher in the WHR systems. So proper soot removing mechanism is required and it is to be taken care during the design as well as the construction side, so that we can operate the entire unit in efficient way. Now I hand over to the Siemens team, Mr. Naulo Kumar and Mr. Sibindra Nandi, to continue their presentation. Please.
Thank you, sir. Marithu sir, can we get the sharing access?
I think now it is okay, sir.
Good afternoon, everybody. Shibendra here from Siemens, along with Navlok.
Good afternoon, sir. Welcome to this Cementech program.
Okay, so let me just share my screen and please let me know once you can see my screen.
Yeah, sir. We can able to see the screen, sir. Now presentation mode also okay.
Okay. Great. So first of all, thank you very much, sir, for giving us this opportunity. A big thank you to the CII team for giving us the opportunity to use practices, the latest developments in the field of waste heat recovery system. Over the next 15 minutes, we will take you through an overview of technologies in the field of waste heat recovery system, our digitalized remote solutions for cement and waste heat recovery plants, other solutions and technologies of decarbonization under Siemens umbrella, and our financial services to support clients in implementing such technologies. The four trends in the energy world are demand growth, which will increase up to 50% more from the current levels by 2040. The decarbonization to achieve concrete emission reduction is very much needed now and in future. The decentralization will happen to master the growing complexity in energy systems as seen in last 20 years. And digitalization is going to change the way we produce, transport, and use energy. So several technologies now exist in the field of decarbonization. These technologies offer a varying range of applications such as power generation, process steam generation, heating, cooling, etc. We will limit our discussion to power generation application. Let us have an overview of available technologies in the field of power generation. Different technologies exist to convert thermal heat to power, such as steam Rankine cycle or SRC, organic Rankine cycle or ORC, and supercritical carbon dioxide cycle or SCO2. The supercritical carbon dioxide cycle is largely in development phase. The ORC-based technology is limited to smaller power generation units rated up to 30 megawatt of capacity and is very commonly used for low temperature waste heat recovery. Currently, only SRC and ORC technologies are fully commercialized, and SCO2 is analyzed in many funded R&D programs, especially in US by Department of Energy. However, due to paucity of time, we will limit ourselves to the most widely used technology, that is steam Rankine cycle, which consists of steam boiler and industrial steam turbine. This is a process flow diagram for typical waste heat recovery system using steam Rankine cycle. It consists of a steam turbine, a generator, air or water cooled condenser, WHR boilers, and other process and mechanical auxiliaries. While all these components play a significant role in overall plant performance and availability, the two most crucial and performance governing components are the industrial steam turbine and the waste heat recovery boilers. Let us have a closer look at our steam turbine offering. Our product portfolio in industrial steam turbine offers a wide product range. The capacities range from 2 megawatt to 250 megawatt. The RPM of these machines varies from as low as 3,000 to as high as 18,000 RPM. The main steam inlet pressure ranges from 10 bar to 180 bar. The injection steam pressure ranges from 2 bar to 3.5 bar. These turbines are manufactured at our state-of-art manufacturing facility in Vadodara plant, Gujarat, India. Coming to the waste heat recovery boilers, a lot of improvement has been made in its design to improve its uptime. As rightly said by Durgaram sir, the biggest challenge in these components when it comes to waste recovery is the dust that they handle. So a lot of improvement has been made in its design to improve the boiler uptime, its response to varying load conditions, and most importantly, to offer the best thermal and process design with same available waste heat. The decarbonization of cement production process starts with waste heat recovery power generation, where we have a preheater boiler, a clinker cooler or air quenched cooler boiler. And these boilers together can roughly generate around 33% of plant's total electricity requirement. However, this is not the end to decarbonizing cement production process. Different technologies exist today to further reduce the carbon footprint, such as by fuel shift to clean fuel like hydrogen, or carbon neutral fuel like biomass, carbon capture technology, etc. It's not uncommon today where the cement manufacturers are blending the total thermal energy requirement by biomass. The extent, however, is still restricted to 20% only. With our vast product With a vast product portfolio and complete in-house engineering capabilities, Siemens can truly be your partner in this journey of decarbonization. Let us see how the next generation solutions are further supporting cement manufacturers in reducing their CO2 emissions. The existing technology is continuously improved to offer higher efficiency. The technology that we have today, if you compare with that 2 decades back, the plant power generation efficiencies, the availability of plant has increased and improved in multifolds. With our best-in-class steam turbines, we offer high power generation with same waste heat. We are continuously investing a lot in R&D setup that we have in India, and we are continuously working towards product development, a new product development, as well as improvement on the existing product lines. This is ensuring us that we stay ahead in technology. We are also developing new technologies that offer superior performance over conventional solutions. These technologies are while in different phases of evolution. Soon they will be brought to real-life applications as well. The remote diagnostic services are improving the uptime of waste recovery system, thereby improving the true CO2 reduction. In the peak of pandemic, we remotely commissioned one of our industrial projects using this solution. For improving the overall plant performance, we also offer tailor-made integrated solutions, such as meeting multiple utility requirements and fuel shift compatible solutions, or integrating the waste recovery system with existing CPP and other utilities. Let us dig a little deeper into our digitalized remote solutions. The digitalized remote diagnostic service offers remote support, operation advice, and predictive analytics to maximize the equipment availability. The rotating assets are the heart of cement plant as well as WHR plant. Our digitalized remote diagnostic service supports in improving the health of these plants. So how do we make it possible? Using MyConnect, we safely gather the real-time data, which is securely stored in our data management system. With our automated data processing and advanced data analysis by our expert diagnostic engineers, we monitor the health of equipment and provide quarterly reports and proactive notifications, including early warning in case of critical changes that develops over a period of operation. How does this benefit you? So the remote diagnostic services avoid trips and forced outages. It provides a smarter maintenance planning, leveraging on OEM design and fleet-wide experience. The analytic capabilities and early detection of issues provide powerful insights and helps in improving the responsiveness in case of an event through advanced remote troubleshooting. With this service, we bring our vast experience to remote monitoring of critical assets. As you may notice, we have more than 17,000 connected assets. We have helped our customers in avoiding more than 500 forced outages. Our team of experts handle more than 500 tickets per month, and we have successfully transformed more than 150 forced outages into planned activities. Now let us have a quick look at our decarbonized industrial solutions portfolio. The path to decarbonization is through 3 avenues as shown here. The first avenue is efficiency increase, which is possible through technologies like waste heat recovery, combining heat and power, seed flow-based power solutions, brownfield engine exchange, by having highly efficient turbines, compressors, other plants, accessories, etc. The second avenue is fuel shift or hybridization, which is possible through technologies like coal to biomass shift, coal to gas shift, thermal storage, hydrogen co-firing gas turbines, etc. The third avenue is to decarbonize, which utilizes clean energy source such as biomass or geothermal, green energy storage systems, solar power, and 100% hydrogen-fired gas turbines. As you can see, more than 50% of our portfolio is based on technology that is and will be relevant in a decarbonized energy world. Now, let us hear from my colleague, Shivendra, about the offerings from our financial services. Over to you, Shivendra.
Thank you, Navlok, for the excellent overview of our technological capabilities. To support all of this technology, Siemens has in its repertoire a basic a service company which is Siemens Financial Services, which clubs financial support to customers with who are planning to use this technology. So it's basically a combined offer of technology and finance from the house of Siemens. Yeah, next. 2011 in India, we started operations as a non-banking finance company under the house in the house of Siemens as Siemens Financial Services, supporting customers who are using Siemens technology. And in that respect, we offer from our own books facilities like loans from our books, leases. Loans are well known to all of you, basically, like any other bank. Leases are only done by non-banking finance companies like us, where we take the equipment from Siemens Energy and we simply buy the equipment and lease it out to the end customer. We also do sparingly underwriting of service agreements, that is, service agreements which Siemens would get into with customers with a defined flow of receivables. We will write the credit risk of those receivables. Other than that, we are also into short-term working capital where we are giving deferred payment solutions to customers, which protects their existing credit lines and gives them optimized cash management to manage their cash while taking our technology. So these are some of the offerings which we are doing under the NBFC arm and supporting Siemens technology. We hope to hear more from you whenever there is a technological solution. There will be a technology plus finance solution from the house of Siemens. If you have any queries, you can get in touch with me, either myself, or my colleague Sangeeta, based out of Gurgaon. So that's it from Siemens Financial Services. All the best to all the participants.
So thank you, Shubhendra. We want to become the most valued energy technology company in the world, and we strongly believe we have everything it takes to do so. With this, we want to thank you for your time and patiently listening to us. For more details, please contact us. Thank you.
Okay. Thank you, Mr. Navlok Kumar and Mr. Sibendra Nandi. You have nicely explained all about your technical solutions as well as financial solutions and the decarbonization technologies like SRC, ORC skills, and the wide range of turbine units from 2 megawatt to 250 megawatt. Even I have visited your Vadodara unit also. I was in Gujarat sometime. Or I visited. I know the technologies adopted over the manufacturing unit. And the preheater and cooler area boilers also you have touched. I really appreciate the 6 remote diagnostic centers, services you have, all those data storage and analysis part. You have nicely explained it. Of course, that efficiency increase and fuel shift, this is very big concern for all of us, those who are working in the industries. We have to consider all those things for our betterment. And very impressive area is this loan and finance, as well as the cash management. He explained it very nicely. Anyway, thanks to you both. Now, I hand over to Mr. Balagurunathan, ESP Technologies, about the ESP technology in the WHRS systems.
Sundaram sir, I think you are on mute. Please check.
Yeah, I'm not in mute.
Yes, sir, I'm talking about Sundaram sir, Balagurunathan.
Okay, okay.
Balagunathan sir, are you there? Sir, Durgaram sir.
Yes.
Hello.
I think we,
Yes, sir. Now it is audible,
yes.
sir. Balagunathan sir.
And I am also visible.
No, sir. The keyboard is visible, sir. I think camera we need to
Yes, sir.
need to rotate.
Yes, your keyboard is visible.
Okay, it doesn't matter. It is good that I am audible. I can continue my dialogue. I would like to introduce myself as Balagunathan, Managing Director of ESP Technologies Private Limited. I'm retired Executive Director from Bharat Heavy Electricals. I worked in BHEL for 38 years, the entire period of my professional career. And a specialist in electrostatic precipitators. The electrostatic precipitator is the most versatile equipment for control of the particulate emission from particularly the cement industries. Because the precipitator offers quite a lot of advantages in the sense that it can be modular in size, then it can be designed to meet any specific conditions, operating conditions like the temperature, flow, and also the required emission. The pressure drop is significantly very low because the flow gas velocity inside the precipitator is significantly very low, less than 1 meter per second. And hence the loading on the induced draft fan of the application, be it a clinker cooler or a kiln or the cement mill, is significantly reduced, and the size of the induced draft fan can be made smaller. Coming to the areas of application, the most common area of application of electrostatic precipitator in cement industry is the clinker cooler. Particularly when the clinker is originating from the outlet of the rotary kiln at a temperature of about 1200 degrees C. It is in modern practice cooled by means of rotary air blowers. So it is like a great arrangement. The clinkers travel over the grate, and the air is blown through from the bottom, and the clinker is cooled to a temperature of about 100 degrees or so. And the air which is used for cooling the clinkers carries with it a valuable material, the product of the industry, namely the cement in a very fine form, along with a certain combustible material from the outlet of the rotary kiln. Many of the rotary kiln are coal-fired, so naturally the residues of the combustion, like the fly ash and other particles, may also get as part of the clinker lump. So the major application of electrostatic precipitator is in the area of clinker cooler, and we have successfully engineered to many such companies like VIII C, particularly the VIII plant. Now, the precipitator technology per se is not very new. It's more than 200 years old, but the major application has been in the area of power generation, and it has spread over to the other applications like the paper mill, cement mill, and so on. Coming to the cement mill, the parameters, the emission regulations are stipulated by the Central Pollution Control Board. and which has been brought in force is 30 milligram per normal meter cube. The permissible emission is 30 milligram per normal meter cube, which is on par with the standards which are prevailing in other developed countries. So the regulations have traveled quite a distance. Originally, it used to be around 100 milligram per normal meter cube. Then it was reduced to 50. The current value is 30 milligram per normal meter cube. And coming to the parameters of the flue gas, like the gas from the clinker cooler, the temperature will be around 260 degrees, which is quite sufficient, quite large in the sense that the mechanical design of the electrostatic precipitator has to be suitably taken care to sustain this temperature of 260 degrees over long periods of operation and also yield the desired level of the emission. The other area of major application in a cement plant is the cleaning of the kiln gases using electrostatic precipitators. Comparatively, the quantity of flue gas handled in the cement kiln is low, but the inlet concentration is quite high. It ranges from 60 grams per normal meter cube to around 70 milligram per normal meter cube. Coming to the topic which has been given to me, the latest development in the precipitator technology, I would like to mention a few which has already been practiced by many of the reputed manufacturers of electrostatic precipitators. The first one is the intermittent charging controllers. So the earlier designs of the transformer rectifiers, which supply the high voltage power supply to the negative electrodes or the discharge electrodes of the electrostatic precipitators, used to convert every off wave to a full wave and make available the power supply on a continuous mode. But over a period of time, developments have taken place, and it has been found that the intermittent charging or the semi-pulsing technology has yielded a very high performance improvement, both in terms of the reduction in electrical energy as well as the reduction in particulate emissions. The intermittent charging means that instead of charging the electrostatic precipitator field through every off cycle, the thyristor is controlled so that it can alter. Hello. So that it can charge the field in an intermittent pattern. Like, for example, we call it a charge ratio. For example, if we take a charge ratio of 1:3, it means that the thyristor or the field is charged only through one cycle out of a group of 3 cycles. And the charge ratio is variable from 1:3 to as high as 1:125 or even 211, etc. So there is a significant reduction in power consumption of the order of about 40% compared to the conventional transformer rectifier set. And there has been a reduction in the particulate emission also. Now, many of the controller manufacturers, like Adore or the DHL, etc., have made it a practice that the transformer controllers are invariably with the intermittent charging controllers, so that the customer get the full benefit of reduction in emission as well as reduction in the power consumption. The second major advantage or the development which has taken place in the recent years is the high frequency power supply transformers. Generally, the old transformer sets operate at a frequency of 50 hertz. stepping up a primary voltage of 415 volts, single phase 50 hertz cycle to as high as 70 kV or 80 kV, depending on the electrode spacing. But it has been found that operating the fields with a very high frequency of the order of 25 kilohertz to 50 kilohertz. So the transformer itself is totally redesigned. And, it operates in a switch mode power supply system, and the power which is fed to the electrostatic precipitator field is at a very high frequency of the order of about 25 to 50 kilohertz. So the high frequency power supply gives an added advantage in the sense that the particles can be charged to a very high level of electrical charge of the coolant, so that the collection of the particles on the electrode surfaces is at a very high, significantly very high level, and also saving in the power consumption. Now, in the case of the clinker cooler application, as I said, the inlet gas temperature is as high as 260 degrees. And in many cases, we have experienced the fly ash or the ash showing a high electrical resistivity. That is resistance to getting charged and migrating towards the collecting electrodes. When we come to the rear field, the last field, much of the collection had taken place in the preceding fields. And the last field is supposed to handle a very fine dust and yield the emission limit of 30 milligram or even lower. So for that purpose, a very high level of charging is required. And the new technology is to go for a micro pulse. The width of the pulse, which is supplied to the electrical field, is in nanoseconds, and particularly when the temperature is very high, of the order of 250 degrees, encoded in clinker cooler application, the multi-pulse transformer rectifiers have been found to be extremely useful. Coming to the last but not the least, I'm happy to say that the whole precipitator operation can be managed from a single source. Though the electrostatic precipitator is located far away from the clinker or from the with the advancement made in digital technology, it has been possible to manage or to control the parameters from a single location, like your unit control room, etc. So the precipitator management system is microprocessor based, and it receives the input from 2-3 sources. Like, for example, if an opacity monitor is mounted in the stack, a signal is obtained from then the capacity of the cement clinker cooler or the kiln, etc. So 2 or 3 inputs can be accepted by the centralized precipitator management system, and based on which the controller, the precipitator management system, central controller will interact with the individual transformer rectifier set, the wrapping motors, etc., and adjust the parameters, critical parameters like the secondary voltage, temperature, the wrapping frequency, etc., etc., so that at any point of time, the set value of 30 milligram per normometric cube can be ensured with a significant reduction in power consumption. So the operator need not go to the precipitator installation nor the ESP control room, which houses the electronic controllers of the transformer rectifier sets, etc. The whole operation of the precipitator can be done from a single location, and it is totally automatic. It is a closed loop system taking the input from opacity monitor and other sources, and suitably interacting with the transformer rectifier controls, tapping motors, etc., and adjusting the parameters depending on the flue gas parameters at the inlet of the ESP, as well as the emission at the outlet. So these are the major advancements which have taken place in the electrostatic precipitator, and of course, my company, the ESP Technologies, the private limited, provides total service, consultancy and engineering services whenever the plant is taken under shutdown, and the electrostatic precipitator is to be overhauled or brought to order so that the desired level of performance is ensured. One more thing which I would like to mention in this context is that invariably any of the cement plant have their own captive power plant. They don't depend on the power supply on the grid because once the kiln is started and it is in operation, the plant can ill afford the failure of any power supply. So many of the cement plants have their own captive power plant to meet their in-house requirement, and the cement plants are invariably a coal-fired power plant. So again, the problem comes at the emission of particulate matter plus the other greenhouse gases like SOx, NOx, etc. There also the similar technology of precipitator is being applied for improving the performance as well as the getting a significant saving in the power consumption. In the modern times, if we were to meet the emission norms stipulated by the Central Pollution Control Board, the requirement of efficiency has grown up to almost ultra high level, 99.95%. Practically 100% of the particulate has to be collected in the precipitators before the clean gas is let off to the atmosphere. And with a greater emphasis on the particulate emission, because particularly the particles of smaller size, like a 2.5 micron, they travel through long distance. So the public or the inhabitants who are close to the cement plant are not very seriously affected, but the people who are located far away, 5 kilometers or 6 kilometers away from the power plant, for no fault of them, they get affected by the fine particles which are being carried by the flue gas stream over the long distances of 3 to 5 kilometers, etc. So there is a need to even control the submicron particles of size 2.5 microns and below. But there is a continuous effort on improving particularly the electrical energization of the electrostatic precipitators. Whatever I have explained, the intermittent charging, the pulsing, the high frequency power supply, and the precipitator management system, they have already been put into use. They have become operational, and the performance of this technology has been proved to be very successful and has become almost a mandatory requirement in many of the large utilities, coal-fired utilities who can afford. The same technology is implemented in many of the cement plants as the capacity of the clinker cooler increases. So it is an opportunity for me to share with you some of the latest developments. And I thank particularly Mr. Marimuthu, who has been highly instrumental for giving me an opportunity to be a part of this presentation. And unfortunately, the video is not working, but I'm sure that I was able to communicate through the audio system the latest developments in the field of electrostatic precipitators. Thank you again once more for the opportunity given to me. Thank you.
Thank you, sir. Thank you very much sharing your vast experiences. Though you have headed as executive director in BHL, really very much good experience you shared with us about the low pressure drop across the ESP and which will lead to high defined loading pattern. Everything is very nicely shared about the power reduction and all. And the intermittent charging controllers, thyristors, really we have already adopted in our ESP. Whatever you are shared, we have already experienced also. Really, it is reducing our electrical energy as well as the particle side reductions. And the single phase to three phase conventional transformers to latest technology transformers, all those things are very attractively you have explained it, sir. Also, the flue gas opacity monitoring system, though which is to be adopted in all the plants, some area it is very lagging also. Anyway, thanks to your good sharing, sir. Now I hand over to Mr. Pankaj Tiwari and Mr. Manish Vijay from JK Lakshmi Cement on their best practices in WHRS system.
Sir, I think you are on mute.
Karna?
Sir, Pankaj sir, who is presenting? Either you or Manish?
We both are presented.
No, sir, but who going to share the slide, sir?
I am Manish will be shared.
Okay, sir, I am giving the access for
Are you able to see my presentation?
yes, sir. Please make it in presentation mode. Sir.
Yes, yes. Now it is visible. Yes.
So thank you, Chairman. Thank you, CIE, for giving this opportunity to JK Lakshmi share our journey or our experience about WHRS system. I am Manish Vijay along with Mr. Pankaj Tiwari and Mr. Vivekanand are here to share our journey of the waste recovery plants which we have installed in the Siroi plant. JK Lakshmi Cement.
To interrupt, can you make it in presentation mode, sir? Then only.
Now it's okay?
Now it is okay. Correct. Yes.
Okay. So, we JK Lakshmi Cement are a part of a well-recognized JK organization, which was one of the oldest industrialization group in India. We have a number of other companies such as the JK Seeds, JK Tire, JK Vikrant, JK Paper, JK Lakshmi, JK Finner, and Uman Dairies. Over all India, pan-Indian cement present capacity is around 12 million ton per annum, and we have a 3 clinkerization units. One is the Siroi, and another 2 is the one in the Durg, and third one is the our system concerned with the Uber Cement Works Limited. Apart from it, we have a different cement grinding units such as
One is installed in Kalol, Gujarat. Second is the Jhajjar. Third one is the Jhajjar, and fourth one is the Cuttack, Odisha. So by combining all these, our cement present capacity is around 12 million ton per annum, and we are here to present our case study about the Siroi plant. The Siroi plant was established in 1982 with one kiln having a capacity of around 1500 metric ton per day, and the years of after number of years, we have installed two other kilns which have original capacity is around 2,500 and 2,595 and 96. And by doing the in-house modifications and the optimization of the kilns and installation of the parallel repeaters, we are able to upgrade our kilns from kiln 1 from 1500 to 4,750, line 2 2,500 to 5,125, and line 3 is 5,125. So I am coming to our topic. What is waste heat? Waste heat is defined as a heat which is not used for further any process or further any application. Like so, in a cement plant, three areas where the heat is generated or which was not used earlier for the any process, something like that. Second is the filter flue gases, and third is the
Mani sir, your voice is not audible.
is the gases and other parameters of the composition of the gases also. The waste heat which is generated from any process can be converted into three types. First, to use for drying of any material. Second, for the refrigeration process by using of the vapor absorption and the vapor adsorption cycles. Third one is to generate the power by the organic Rankine cycle or the normal Rankine cycle. These I have already told you that in a cement plant, basically three heat sources are there: cooler outlet, kiln shell, and the filter flue gases. Now come to the history of the JK Lakshmi. Uh, uh, I am very happy to share with you that we are very fortunate that the JK Lakshmi cement is the first few cement industry who has installed the waste heat recovery project in the 2000, had taken the waste heat recovery project in 2008 and installed in 2010. As a dry state, as a Rajasthan state, we have a limitation of the water sources. So our company has decided to install the air-cooled condenser in place of water-cooled condenser and save around 2 lakhs liters per day. As we have a three kilns, so the in a initial mode of the decision of the to install the boilers, we have decided to install in all three kilns. But as we had already done a fly ash dryer system to dry the fly ash system in our line 3, so we choose three preheaters in our kiln sites, and line 1 and line 2 is for AQC boilers. The total generation capacity is around 15 megawatts by these 5 boilers. These are the views. These are the horizontal boilers for the preheater side and the vertical boiler for the AQC side. These are the our experience which we have faced during the commissioning or the stabilization of the WHR process. First is the malfunctioning of the damper. As we all know that the damper is a critical part for our cement industry, and if they are malfunctioning, then it can stop the plant and damage the system by damaging the ducts and other things. So that we have also faced during the initial stage of the plant. Is because of the damper was actually closed by a certain limit, but it is showing in the open position in our DCS CCR, and the pressure drop across the boiler was very high, so the plant was tripped. To get rid of this solution, to get rid of the problem, we have done the brainstorming and is decided to install the limit switches and put a logic. Then whenever the limit is losing or just bypassing, then the over bypass damper will open. So by this we have systematically commissioned over WHR. And the second problem which we are facing during the commissioning is the boiler outlet temperature. On the Peter side, it was higher side than the design temperature. It simply means that the gases was bypassed from the boiler. To get rid of, we have discussed with the suppliers, and our internal team has decided to provide a path for the gases to get the maximum recovery from the gases to the water tubes through the steam tubes. By installation of the baffles, we have improved around 5% of our power generations in our boilers. Second, as cement plants are working in the negative suction mode, so the leakage also play a vital role in the power congestion of the Peter fan as well as the productivity of the kilns. And if any leakage inside the boiler, it will also impact on the steam temperature, and it will also directly impact on the power generation. So the same we were facing during the over commissioning time, that boilers were
Mani sir, your voice is not audible.
power generation as well as the reduce our Peter fan power. By capturing the false air regression, we have generated around 4% in the power generation. Fourth one is the bypassing. As in the bypass, we have a multi-lower dampers. So the sealing of that damper is not such way that it seal 100% of the gases. So by doing the brainstorming sessions and other things, and the experience of our mechanical engineers, we have decided to put a plate above the flanges of the damper, so that during the closed condition, no gases will be bypassed through this damper. By doing this, we have got a tremendous result in generation of the power, and the power will generate around 30% higher by sealing of the damper from the Peter side. It is very tough to do the maintenance of the damper during the running conditions, as we have a lower dampers earlier. So by doing, and we are facing continuously problems in the damper for the leakages, internal as well as externals. So our team has decided to replace this damper with guillotine dampers. By doing this, we were able to sustain our generation continuously. Now I would like to call my colleague for further explanation.
We have installed WHR in Predator and Cooler in all the 3 lines with 5 numbers of boiler, and the generation capacity was 10 megawatt. Further increase the power generation during the capacity upgradation of our line 1. We have installed 1 additional boiler, and the capacity increases up to 12.5 megawatt. For further increase in green power generation, in 2018, we have introduced a hot area circulation system and increases the power generation up to 14 megawatt. Recently, we have installed new boiler in cooler and feeder of line 3 with a capacity of 10 megawatt capacity. And current generation is line 1, line 2 is 11 megawatt, and line 3 is 9 megawatt. With the installation of hot air circulation, we have following challenges: high clinker temperature that will affect the operation of cement production, Second one is how many cooler fans should be connected to hot air recirculation, selection of fan motor to handle both cold and hot air, selection of fan to handle high dust concentration, how to take care of sensitive hot and to mitigate this challenge, we have connected hot air duct to cooler fan number 6, 7, and 8 only to go with fans for high dust concentration and operating temperature is near about 140 degrees Celsius. Motor rating as per maximum power demand in cold air condition and availability of only 2 movable parts in ICAN cooler reduce the chances of damage of sensitive parts. With this installation, we have increased our increased by 10,000 units per day, more wind power generation. Now, my colleague, Mr. Vivekanand, will share the initiative taken to reduce the auxiliary power consumption.
VFD installation in VAP and CEP achieved auxiliary saving is 336.72 kilowatt, and in CEP 307.2 kilowatt in a day, VAP and respectively. Earlier, this is the 55 kilowatt VAP and CEP is the 90 kilowatt VFD. We installed a turbo vent fan over the turbine roof, and we saved 73 kilowatt per day. And HVSV lights replaced lights. Benefit is around 10 kilowatt auxiliary power per day 10 kilowatt auxiliary saving. New auxiliary saving ID fan and motor installed in AQC 1A and B boiler per day saving is 1.2 megawatt. That is in terms of 1,200 kilowatt per day saving. In all lighting taken in auto mode, auxiliary reduced approx 30 kilowatt per day. We are putting a timer on this system. New IR compressor installed and commissioned for power saving. Per day is 3.26 kilowatt per day saving. And auto start and stop exhaust fan of air compressor, which is running continuous 3 fan, now running only single fan, auxiliary saving approx 24 kilowatt per day. Some modification we did in ACC. Some created under ACC building for decreasing the ambient air temperature and thus for better efficiency. In AQC2 boiler CPH line, new MOE installed for better performance CPH. In all cooler boiler, DCC external support fabricated and installed for increasing the reliability of DCC links. Angle covered on superheater coils for prevent the coils leakages. New isolation wall installed in PH2 boiler for eco bypassing the for purpose of leakages. Air blaster installed in all preheater boilers for prevent dust in deposition in the eco coils. In AQC A and B boiler CPH line, new MOE installed for better performance of CPH for operation purpose. Boiler, both RC pump heat exchanger modified for better cooling of mechanical seal and prevention of line leakages and problems. Boiler condition preheater line modified and used as an economizer, and 1 ton steam increase for boiler performance is increased. TG temperature logic changed to previous 280 degree to 356 degree, revised to 300 degree centigrade to 400 degree. Benefit turbine tripping reduced and reliability factor is increased. I call Mr. Manish for taking the further.
These are the figures which we have achieved for the last 3 years. And the corresponding CO2 emissions which we have reduced by opting or generating power through the WHR green power generation. And in the last but not least, I would like to conclude in this that the designing of the WHR is an essential or critical factors for generation of the power. Before designing of the boiler, you should know how much heat is required for drying of the raw mill. So if you know about the exact amount and how much it is required, then we will able to ascertain the temperature drop across the boiler, and the boiler should be designed accordingly. This will be helpful for us in our line 3, as in line 3 we have installed a new boiler on the temperature, outlet temperature in the range of 160 degrees. Again, earlier it was designed for 205 degrees centigrade, and the AQC outlet, boiler outlet, earlier was designed for the 120. Now we are operating at 75 for a new boiler. This will help us to reach our kiln 3 WHR generation in the range of 38 to 40 kilowatt per metric ton, as compared to our earlier WHR generation of 24. So now combinedly we have reached around 33 to 35 kilowatt per metric ton of clinker through the WHR. Thank you.
Thank you, Mr. Pankaj Tiwari and Mr. Manish Vijay and Mr. Vivekananda. Nicely explained about your 40 years journey of the entire JK Lakshmi unit and the 3 locations where the sources of heat can be taken out for the WHRS. That schematic diagram is very nicely prepared one. About the air-cooled condenser, the saving of 2 lakhs liter per day water saving is good initiation done by you people. And the case study about the malfunctioning of the dampers due to high DP across the WHRS and the false air ingression, all those things nicely captured in our PPT. And one more attractive information you have given, that multi-lever damper to gelatin damper you have switched over. That is very good information for all of us. Another one, that hot air recirculation adopted and the challenges. By this way, you have highly generated around 10,000 units per day. That is also one good initiative. And all the bullet points which is covered in your auxiliary power savings, really very good initiations done by you people. Oh, only some 2 questions I have regarding that superheater coils angle covered to prevent the leakages. That MOC, material of construction, you can share it if possible. Another one, that baffles you have used to control the boiler outlet temperature, that baffles materials also, MOC, material of construction. These 2, if you share, it will be good for all other people also, as a knowledge sharing point of view.
For baffles, the material is the T12 material we are using in baffles. In
Okay.
separator coil, it is made also T12 for covering the angles. Because of there is a clinker gases, clinker is deposited in the coils. That's why we are provided over the separator coil. It
Yes.
that the clinker it cannot be hit to the directly to the separator coils.
Yes, yes. Like sleeves we are using in the bed coils, normally we provided the sleeves. Stainless steel sleeves, you have used the T12 material.
Yes.
Yes, yes. Okay. Thank you. Thank you, all 3. Thank you. Now, I hand over to Mr. Marimuthu as CI on best practices to improve the performance and WHR systems. Now you can proceed, Mr. Marimuthu.
Thank you, sir. Once again, good afternoon, all. I have been working with CA for the past 1 year, and I have around 7 years of experience in the power plant related to AFBC, CFBC, and this, WHR boilers. In this section, I'm going to cover the opportunities for WHRS performance improvement. So already already the points put up by Manish are valid, and in addition to that, I'm going to add some of the points which are also to be followed or to included in the daily basis, and even for while designing the new WHR boilers, those points also need to be taken care. So in this presentation, I'm going to cover some of the opportunities We know nowadays many cement plants already started installing a WHRB. So this study going to give the performance of the existing units and also the latest technology which will add some more improvements that is to be adapted by the cement plant WHR units. This will cover. So this is the outline. First one is waste heat source in the cement plant. So this will give the where we are getting the waste goods in the cement process. Then second one is about the heat availability and the power generation potential. And then other one is analysis of design and actual performance parameters. Then parameters that affect the performance. Then on opportunities to improve the performance. Then improve the efficiency of the waste heat recovery system. Then on cement production and waste heat recovery potential. First, coming to the waste heat source in the cement plant, as already the point put up by the Manish, I'm going to add some more point. In the cement unit, the for production of 1 kg clinker, the theoretical heat required is 390 to 420. So, but actually, what we are achieving is around 720 kilocalorie per kg of clinker. In some units, it's around 680. In some units, we are getting 750 also. So, in the average, we are getting around 720 kilocalorie per kg. In this 720 kilocalorie, we are utilizing only 58% for clinker production. Remaining 42% we are wasting. In this, some of the unavailable losses are radiation loss, fuel and raw mill moisture, and fuel and raw mill moisture evaporation and clinker heat. And the recoverable heat is cooler exhaust and preheater extract we can recover. So this is the simple process diagram from the clinker cooler and preheater stages. So in this, on the right side, you can see the AQC boiler is normally designed for the flow of 0.8 to 1 nm cube per kg clinker. There we will have the heat around temperature of 350 to 400 degrees centigrade. And in case of pH boiler, we are having the flow of 1.4 to 1.6 nm cube, and there the temperature around 280 to 350 degrees. So these systems already adapted in many of the units. The one more areas which we can explore is tertiary air tapping, and there we have potential to explore. So there we will have the volume of hot air from 0.5 to 0.6 nm cube. The temperature will vary from 900 to 1000 degrees centigrade. Then next on the heat availability. Just a while. Next on the heat availability and power generation potential. Now this picture illustrates the heat available in 1 million metric ton per annum of clinker. For example, preheater gas in the 6-stage preheater, we will have around 17.5 million kilocalorie at 1 million ton per annum. So this heat we can utilize some amount of heat, as we know it is utilized for raw mill drying, and the remaining heat we can utilize for WHRS. So the preheater gas usage mainly based on the raw mill moisture. If you have more moisture, we have to utilize for drying, or otherwise you can use for power generation. And on the clinker cooler side, if we consider third generation cooler for 1 million ton per annum clinker generation, we will have a heat content of around 9.4 kilocalorie. So what I'm coming to say is for the waste heat recovery for generation, based on our study which we conducted in 6 to 10 units, so electrical generation possible for 1 kilowatt 130 to 140 million calorie we need. In terms of clinker, 25 to 40 kilowatt metric ton of clinker is possible with the heat with the heat from the preheater and cooler exhaust. Then coming to the cement production and power generation potential. Based on the cement production category, now based on the installed capacity, we can generate up to 540 million tons. So, but we are actually now generating between 295 to 350. So the last financial year 2021, we achieved around 350 million ton. So these figures we used for finding the WHRP potential across the India for considering 35 kilowatt per metric ton based on the installed cement production capacity, we can achieve around 1,500 megawatt, whereas we have installed a capacity of 800. So still we are having around 700 megawatt potential. So in this, we have consider the heat which is required for drying process, so we have neglected. So considering this, so we can we are having the potential further around 700 megawatt. Next is on the performance parameter, means best figures. To find out the potential in the waste heat recovery system and to find the performance of the waste heat recovery system, we have conducted study in 6 to 10 units. So based on that, we have arrived the best figures from the 6 to 10 units. So in that, the criteria what we consider is age of the unit 2, 5, in between 2, 5, 10, 15 years, and also the manufacturer is different, and also it considers 5-stage preheater or 6-stage preheater, and also the different clinker production. So based on that, what we brought is for the power generation, best figure which we seen is 43 kilowatt metric ton, 43 kilowatt per metric ton of clinker, and the heat for uh, uh, based on heat 145 kilowatt per million kilocalorie heat, and the thermal specification with the WHRS, the best which we seen is around 713 kilocalorie per kg clinker, and turbine heat rate best we seen is around 3500. Overall efficiency of the system is 23, and APC is around 4.1%. This is the data which we collected from the 6 units. Clinker production to power. So on the left side, the yellow color indicates the clinker production TPD 3, 4. For example, 6-stage preheater 3450 is the actual production. So there they were getting 6.2 kilowatt. There only the best figure we got around 43 kilowatt per metric ton. Whereas in other units, the power generation is less. There we found some of the difficulties in the existing operation. So that time, once we run the slide, we will also come to know. So in the coming slide, I will give the whatever the problems which is being in the operating units. So I will clarify. So based on the table, the average power generation from WHR in India is around 35 kilowatt for metric ton of clinker, and power generation is one of the unit is more than 40 kilowatt per one, where the where there is a more waste heat, means about greater than 300 kilocalorie per kg. So whatever we thought, as I said, around 42% of heat we are wasting into ampere. So in this some avoidable losses is there. So in that avoidable loss, suppose if it's greater than 300, so it can generate 40 kilowatt. And if the overall efficiency of the WHR is good, then this also add value to generate, and better heat utilization in the boiler also factor. Then this table gives figures on boiler and turbine parameters. So the overall efficiency of the system for based on the different cement production capacity is illustrated. So it is in the range between 60 to 23%, and power generation is around 120 to 140 kilocalorie per million kilocalorie, and the turbine heat rate which we found is around 3,627 to 4,120. So this is turbine heat rate calculator based on the considering condensate heat enthalpy. Then coming to the parameters affecting the waste heat recovery system performance. So the first one is low heat input to the boiler. The parameters that affecting WHR is in some of the units the design megawatt is one, but actually we are generating maybe less or more, and some factors which influence the less power generation. So those things is covered in this slide. So first one which we are going to see is low heat input to the boiler. So for the low heat input to the boiler, based on our study conducted, what we conclude is first one is mismatch between design and actual heat input to the boiler. Mismatch means at the design stage, whatever the heat, waste heat which is coming from the cooler or preheater which we consider is not matching with the actual. So that gets reduced with the generation. Then the another one is false air ingress. As Manish said, so if false air is there, definitely it will contribute in auxiliary power consumption and also to the power generation, because if the false air ingress is there, it will increase the volume, so it will affect the heat transfer, so it will reduce the power generation. And another one is bypass damper erosion. So generally we will have a bypass damper for the WHRS, because it deliver heat for the raw mill drying, so we have to open some amount of air for drying. And also if you want to maintain the temperature, in that case also we have to use bypass damper. So this bypass damper erosion, only when we record that time it's open, okay, but during the normal operation if it is leaks, so it is allowing the waste heat to the ambient, so instead of power generation. So this also one point. And another one is slagging and fouling. So if slagging is there, so definitely you will cause the reduction in heat transfer, and it will also reduce the power generation. Then another one is fluctuation in boiler process parameters. So we know the many of the cement units installed in late 2000. So nowadays the latest technology come for the PIDs. For example, variation of control valve, and variation of fuel feed, and variation of uh, what is it? That control valve, and mainly in the control valve, and variation of the fuel feed. The first point which we are going to see is untuned P&I loops. If the P&I loops are untuned for the latest technology, definitely the variation in the control valve and variation in the damper operation, the fluctuation in that variation will be more. So this will reduce our power generation. Means this is the one of the factor contributing in the reduction of power generation. And another one is change in production rate. If we frequently change the production rate, so that will also affect the WHRS power generation. And disturbance in fuel feeding. Suppose if we are if we are mixing the high GC fuel and low GC fuel, definitely the mixing will not be proper, so it will it will change the heat input to the kiln. So the heat which is coming from the cooler also will vary depend upon that. So that also vary at our WHRS production rate. Then next on the high pressure drop across the boiler. So generally high pressure drop occurs if there is any disturbance in the flue pass system. For example, fouling and slagging is there, or any additive dust in the cooler dust, so that will also cause fouling. Then high pressure drop will occur. And high cooler exit temperature and slagging nature. And based on the study conducted in the 6 units, we did not find the temperature to the WHRS greater than 600. So, we did not identify any slagging or fouling nature dust in that boiler. So, but in one of the unit we have observed, so where the temperature is greater than 600 degrees centigrade. So there the slagging has occurred, and it has caused a high pressure drop across the boiler. And another one is high dust concentration in pH exist gas. Suppose if the dust concentration is more, so what will happen? So it will foul on the tube, and it will reduce the heat transfer. So this is mainly because if my cyclone is not giving its efficiency as per the design, or if my dust collection system is not good, so this will happen. And another one is low mainstream temperature. So low mainstream temperature, it's normally occur due to low clinker production. If my clinker production is there, we cannot say my mainstream to reach the design. So if a low clinker production is there, then my heat input also less. So so temperature will definitely less. And low cooler exit temperature. So if my cooler exit temperature itself less, so instead of, for example, 400, I designed my mainstream temperature should be 350. If I'm giving 350, then my mainstream temperature will not 350. So this is also one contributing factor. Then next one is low cooler exit volume. As we discussed in the design stage, the volume which you are getting from the cooler mid tap to the WHRB should match with the actual value. So if it is there is a mismatch, then definitely this temperature we will not get. Then another one is bypass temper erosion. The bypass temper erosion might be due to the high concentration in the gas or air, or it is due to the throttling operation. So if you are operating the damper with slight bypassing, maybe 10% or 20%. So in that opening, the velocity will be more. So because the vacuum to the bypass damper will be more than the WHRS system. So it will suck more air from the damper only. So it will automatically increase the velocity and it will cause the erosion. And low resistive material consideration. During the design stage, if the damper is not designed with a high resistive material, so high resistive material to take care of the dust, so it will cause the erosion issue. Then another one on boiler tube failure. Boiler tube failure mainly occur due to the uneven gas distribution and ducting defect. So if the gas distribution is not good, so at some area we will get more gas, so it will cause more velocity. So definitely the erosion will take place. So this is the one reason we observe. And another one is high cooler gas temperature and volume. So if more than design, suppose if you want to operate the WHRS for more than design, instead of suppose 10% or 20% more than design, if you want to operate, so that will allow more fluid gas. So if the coil are not designed for the less velocity, then we will have more velocity, and definitely it will cause erosion. And another one is high dust concentration, we already discussed, and low overall efficiency. So for low overall efficiency, part load operation can be the reason, or turbine aging. So because we have installed WHRS around 2005. So the turbine which are all old may need upgradation based on the efficiency which is giving. So turbine aging also one contributing factor for low overall efficiency. So these are all the parameters which are affecting the WHRS. So where we were not able to achieve the generation as per the design. The next, coming to the opportunities to improve the performance. First one, low heat input to the boiler. Suppose if you are getting low heat input than the design. So what we need to do is recirculation of boiler exit gas to clinker cooler to increase the cooler outlet temperature. So as Manish already discussed, so recirculation also helpful for increasing the heat input to the WHRS, so which helpful in power generation. Then next one is high wear resistant material damper construction. Because if the bypass happens, so part of the amount of gas will be went to the stack, so it will not contributing in the power generation. So we need to take care of high wear resistant material for damper construction at the design stage. The next one is fluctuation in boiler process parameters. And nowadays, technologies are come up with advancements in the PID controller. So addressing the fluctuation in process control using advanced PID controller will helpful. So PID loop performance assessment tool is there. So which act as a tool and which helpful in the variation of this control valve and damper with a minimum variation. So it acts as a tool and to vary to help in varying with minimum variation. So this can be done. So if you have fluctuation in boiler process, then another one, high pressure drop across the boiler. So in this the study conducted in 6 units says there is no defect like this. So if we have any high pressure drop, so we can go for a CFD analysis for improving the dust collection collection efficiency, and also for WHRS boiler. Then low mainstream temperature difference. So for low mainstream temperature, as I said, if the design consideration and the actual heat input is a mismatch, then this can happen. So maintain the boiler and the inlet air gas parameters as per OEM. Or if the problem is present, then we can go for vent air recirculation to increase the mainstream temperature. The next on bypass damper erosion. So nowadays ceramic lining in damper frame for erosion protection is available. So we can go for that. And dampers also available with zirconia liners for the flaps. So that also we can use. And boiler tube failure. So boiler tube failure, as we discussed, the cause will be due to the uneven gas disturbance. So for that we can go for CFD analysis if we have if we are having frequent failure. This is mainly applicable for the erosion point of view. And another one is a low overall efficiency. So for low overall efficiency, if turbine aging may be the reason, or I am maybe getting the low input steam temperature. So in this case, the nowadays turbines are coming up with the latest technology. So improving blade and seal concept provide highest efficiency. So with the latest technology, the old turbines can be retrofitted, and it can we can improve that efficiency by 2 to 6%. Then coming to the improve the efficiency of waste heat recovery system. So first one is about the uh, cooler boiler exit gas recirculation for enhancement in WHR output. So the left figure gives the idea on normal cooler without any recirculation or without any WHRB, and right side cooler figure recirculation cooler gives the process diagram with cooler air recirculation WHRB plus vent air, means stack air recirculation. So with recirculation, without recirculation, now I'm going to give the small brief about what with recirculation and what without recirculation, how it helps. For example, conventional AQC boiler arrangement, hot gas input to the boiler from mid-air turbine and cooler vent air. So gas from the boiler is vented around from 100 or 130. And suppose if you bypass some amount of air, so it will be sometimes 145 also. So in the recirculation cooler, what will happen means part of the hot air from the stack, means after the ESP, which will be recirculated to the middle fan of the cooler. So where only our tapping is taken for the WHRB. So if we instead of giving the ambient air, if we give the hot air, what will happen? So it will increase the heat input to the WHRB. So this will help in power generation. Means it will help in increasing the generation. So this is the simplest diagram of hot air recirculation arrangement, which is done in JK Lakshmi cement. In this, from the cooler mid-up, we have first a detester, and there is a AQC boiler. After that, we have a electrostatic precipitator. So in the electric, whatever the dust fine is collected, it is moving to the clinker silo. Then it is went to the stack. From the stack, whatever the gas which is that might be having a temperature of 100 degrees centigrade will be recirculated to the middle fans, fan 6, 7, 8, where only the tapping for the AQC boiler is taken. So this is one of the case study from JK Lakshmi cement. So in the left side figure, we can see the recirculation duct from the stack, which is given to the middle fan of clinker cooler. On the right side, the new fans are there. So hot air recirculation in fan numbers out of 10, for 6, 7, 8, we have given the hot air, and it was commissioned in the January 2018. So it has given it has increased the output, and has given the savings of around 9,500 units per day. So it also helped in 12,000 kg CO2 per day. These are all about the benefits achieved from the hot air recirculation for the unit of 5,000 TPD. So in this figure, we can see without hot air circulation, the mid-air to the boiler is around 390. So with hot air circulation, around 4 tons, around 220 degree it gets increased. So hot air temperature, instead of giving ambient 30, and we are given around 130 degrees centigrade. So increase the air temperature, it also increase the clinker temperature. So around 20 degree, it increase the clinker temperature. And the steam generation, existing case was 24.7, and with the hot air circulation, we achieved 27.23. So around 2.5 tons. It has increased. So power generation also around 0.42 megawatt, it has increased. So total power generation, total power gain which we get is around 9,500 kilowatt, and also we got benefit in CO2 reduction. So the total saving was around 17 million per annum at the power price rate of 5.5 rupees per kilowatt. So total investment is 22, payback is around 15 months. So point need to be addressed is if you go for a hot air recirculation, heat sensitive parts under the crate to be taken care, wear and temperature resistance fan required because it is coming with maybe it gets some dust and also temperature is more. So fan power consumption will definitely increase because as the temperature increases, the volume of air also will increase. So maybe new fan also will require for this hot air recirculation. Then second one, the area where to explore tapping from tertiary air for enhancement in WHRS output. So in the tertiary, which is having around the temperature of 800 to 1000 degree, which is we are giving to the call signer. So flow which we get is around 0.5 to 0.6 nm per kg, and the boiler. So after giving to the boiler, the exit temperature to the call sorry, the temperature we given to the call signer is 450 to 500 degrees centigrade. So this is based on the case study from one plant. So this is the normal circuit. This is the area for tapping up WHR between the hood means clinker clinker cooler hood to calciner, and the tapping is taken. So this is the circuit so this is for the WHR boiler. So inlet condition airflow is around 0.5 nm per kg. So temperature 945 degree, and outlet condition the airflow is same and temperature is 460. So this is a drop in the WHR. So output what we get is around 4.1 megawatt. So this is the calculation which gives a payback period and the improvement in power generation as well as savings. So with a drop of 945 to 460 degree. So for the 5000 ton production, we will get the power generation of around 4.1 megawatt. So but the thing is we need to add more heat input to the call center because we are extracting heat which we go into the tertiary air to the boiler, so it will increase the some amount of specific heat consumption. So the savings calculation is present there. So for example of thermal price of 1306, we will get a savings of around 266. So nowadays coal prices are increasing. Suppose in case of 2000 or 2250, if the grid cost which we are getting from the government, so if it is 6, so we will be on loss. So in case of the grid cost also increases, so we will get a gain. So before going to that, we need to do the analysis based on the available grid cost and based on the thermal cost. So this has also increased the power generation and also cost savings. Then this is on the benefits about for example, if we are if we are able to produce 10 megawatt from WHR with the TAD, we can produce around 50% of total WHR, and gross output from the WHR with both combining tertiary air, cooler, mid tap, and pH gas, we can reach up to 50. So best figure we have seen is around 43, and average we have seen 35. So with adopting this one, we can achieve up to 50 kilowatt per kg of clinker. So points need to be addressed is because the part of the heat which we giving to the call signer taking for the WHR, so the specific heat consumption will increase. So this is the case for 5000 TPD. And additional pressure drop in the pH due to more combustion gas flow we have to take care. So additional pH fan power consumption we have to take care. If you want to add more heat to the container, definitely coal will be required. So coal grinding power we need to care, and the loss in pH margin for high production due to increased gas flow also to be taken. So because by neglecting this, the power generation was 4.1. So around 10% maybe for this auxiliary as high as so there will be gain, but we need to analyze the thermal cost and the grid cost. So if it is beneficial, then we can go for that. Then third one about improving the WHR turbine performance. So power generation from WHR steam. SRC is widely used for steam Rankine cycle is widely used for WHR power generation. So we see in like conventional turbine, it is not like a conventional turbine. It has some different arrangement to handle this low pressure steam. So generally for a low pressure area, this is called to get maximum efficiency, the injection type condensing turbines are used. So in WHR, we will get the high pressure of around 12 to 18 atta, so 340 to 350. And on the low pressure side, we will get up 2 to 3 atta, that is also 175 to 195. So this is giving us a injection conducting turbine. This is given as a injection team for power generation. So if you look into the power plant, the most of the loss coming from the turbine, because there only we lost our latent heat. So if the enthalpy difference which we are giving to the turbine input and turbine output is less, so automatically the efficiency will be less, because if you take conventional power plant, the efficiency vary between more than 30 to 40. If you go to ultra capital, so there the efficiency will be around 41. But in case of WHR, we will get around 20 to 23 degrees Celsius. That is due to the less enthalpy difference. Now you can see in the table on the left side. So if the temperature is high, mainstream temperature is high, so my cycle efficiency will be 33. So if it is less, for example 13 bar and 350 degree, the efficiency get down. So if the enthalpy drop is less, more steam will be required to produce the same steam. So that's why we are getting low efficiency in the WHRS turbine. So conventional turbine efficiency is around 78 to 84 based on inlet and outlet condition. So with the latest technology, there is a scope for improving the efficiency. So that is by how flow path, either flow path change or partial revamping or footprint replacement, or with the control upgrade. So this 2 to 6% efficiency is possible in the existing turbines. So this is the based on the study, some of the best figures. So the heat rate and internal efficiency of the turbine. So conventional turbine is around 78 to 84. So with the new technology, turbines are available with the internal efficiency of 89 and 88. So heat rate also around 3,500 kilocalorie. And this is the one case study based on retrofitting. So you can see the figure plant 1 and plant 2. So it was designed for around 8.55 megawatt, but it has to operate at 6.52 due to low generation. So generally, if the load factor of the turbine is less, so it will reduce the efficiency. So to operate at low load, the turbine is retrofitted. So with the same stream flow, which is generating 6.52, after retrofitting, it has given around 6.82. So there, the gain of around 0.3 megawatt achieved. In the case of plant 2, 16 designed, and they were operating 11.6. So to increase the internal efficiency, the retrofit was done, and it has increased around 0.5 kilowatt. So what I coming to say is, with the latest technology, there are options to increase the existing turbine efficiency by 2 to 6%. So before going to conclude, I will give small figures on cement production and WHR potential. So from the figure, we can see the year by year the cement production rate is high. So from 291, it's start increasing. So in the financial year 22 and 23, the expected cement production is 381. So and so waste heat recovery potential up to the financial year 21, installed capacity at 520. So this is at 40 plants, and the under plan is around 175. So major cement plants already started started installing new WHRBs. So potential based on cement production of 350 million ton, so 800 megawatt is possible, but by installed capacity of 545, around 1100 megawatt is possible. So why the WHRB we have to go is because of the operating cost. Like a captive power plant now, due to coal crisis, the power cost is just more than 6 rupees. So generally we get between 4.5 to 7. But in WHRS, the operating cost will be 0.5 to 1.4. So with the WHRS, the 20 to 25% of total cement plant consumption we can manage, and also it reduce the power cost by 14 to 18%. So out of 100%, 20 to 25% we can go with this WHRS protection. So and the investment for WHRS we need around 8 to 10 crore per megawatt, and for the CPP it is around 4.5 crore. So So, but considering cost, the many units are lag for installing this WHR. But nowadays, due to the initiative of decarbonization, many plants started installing WHR. So next, this is about the. This is to summarize. So based on the study conducted, there is a significant potential to improve the performance of the existing system. So we have around the scope for 2 to 3% with nil investment by studying the existing performance parameters, and with the payback of 2 years, there is a scope for improving the 5 to 6%, and also there is a scope for greater than 50% improvement with the payback period of less than 5 years. So CA will be happy to conduct a study at your installation. So it will involve performance study, potential analysis, and capacity selection. So best technology identification. So we will help you to study your existing performance parameters, and also we will give you suggestions for the improvement options in terms of this payback and also with the nil investment. With this, I am concluding my presentation. Thank you for participants and for the speakers. Over to Durgaram.
Thank you, Mr. Marimuthu. Thank you for the very much detailed presentation. Really, it was having very good data also. Lot of data you have captured in your presentation is very much useful to all of us. You have covered the theoretical and practical specific energy consumption, and the very good information about the tertiary L2 boiler that is to be adopted by all of us. And the data you have shared about the scope of installation around 700 megawatt, the potential which is available in the WHRS system, and very good best performance because I noticed that auxiliary power consumption 4%. That one unit somewhere you have noticed, you have captured.
Yes,
also. Normally 5%, 5.5% only we have crossed over, but 4% is the very good auxiliary power consumption. And the parameters which are affecting the performance, that slide is covered very good, all the issues and all the remedies. Same the opportunities to improve, like recirculation, high wear resistance material. That's why the MOC I asked with the JKLHME people. The MOC is very much important before selecting the dampers area and erosion areas, and the CFD analysis also. Yeah. And this conventional turbine efficiency and further improvement of 5% efficiency, that is also, you have nicely explained it. Anyway, thanks to Mr. Marimuthu once again.
Thank you.
Now, I hand over to Mr. A.V. Anguraja, Vice President, NIJEC Heavy Engineering. Sir, you can please share your presentations.
Good afternoon, panel members. Good afternoon, participants. This is Anguraju from ISRAC Heavy Engineering Limited. I am responsible for the all type of waste heat recovery boilers. Okay, now so almost now the previous speakers present, especially Mr. Marimuthu and Mr. Manish, they covered most of the things what I intend to talk about it. Anyway, we will run through our presentation. Then we may, myself, I will be more addressing on those queries arising out of these two presentations. So just I will go to my this thing. I am just trying to locate my.
Okay, sir. Nice. Yeah, sir, it is visible. You can make it in presentation.
Yeah. Trying to make it's in peak. Oh, right, that's fine. Now I got it. Fine, now it is visible, no? My screen is.
Yes, sir. Now it is great. Yes.
Yes, sir.
Now I run through this. Basically, this outline covers the left side is the pH, pH boiler, preheater boiler. The right one is AQC boiler. It covers it. Okay, this since already we discussed about what are the heat sources available in the cement industry. Anyway, there are two sources. Also, there are other sources within the plant. The main sources are from the preheater, and the other one is from air changing cooler. Now, this is a diagram. Already we've seen what both of them are presenting. This from preheater, we'll be putting preheater boiler. This preheater exhaust, temperature ranging from 280 to 330 degrees centigrade. Whereas the cooler vent gases are 250 to 300. Nowadays, with various mid conditions, even the temperature goes up to even 600 degrees centigrade as a maximum. There are few plants they are operating at the very high temperatures based on the tapping, location. Now, this was the brief what Mr. Marimuthu covered, like earlier practices and the new practices. Earlier practices, mainly we were focusing about, drying of this, the hot air required for the drying and also fuel consumption basis. But the current trend is mostly on the focus shifted to power generation. Also the plant performance and efficiency also. So like whatever the factor I have given about the traditional heat input parameters ranging from 0.65 to 0.7 kg of clinker, then 400 to 450. These all data is very elaborately discussed by already presented, so I don't want to repeat. So I will go with certain the boiler features. Now this is what the condition what we discussed. The first traditional way of taking the tap off, that is only the vent. It is taken to the recovery boiler. Then subsequently what we were discussing about this ESP, air circulation to whatever this exhaust gas circulation to this fans to improve this efficiency of the system. Also increased power output, which we discussed. Then the other condition, mid-air tapping boosted up with the external hot air generator. We supplied such a boiler also to one of our customer where there is no, the system comes where there is no internally any other power plant. That means they depend on only this recovery power generation. So they will be augmenting the power generation by putting a hack. So supplied such a boiler also, system also. Another one is what we are talking about. This one, meta tapping with from taking from recuperation zone. Also, the quantity, the generation increases by using this for hot air generation. The combination of both. This data is okay. In the general data, what we based on the various cases, the flow diagram we see that how the power generation increases. Then what are the additional impacts in this? If you see this additional impact in some cases, there is an installation cost, and also there are other operating conditions like wear and tear and other things. We go for a hack. What is the additional investment? Then coming to tapping from the recuperation zones, then coming to the fuel consumption. That is overall plant efficiency of this. Balance between the fuel consumption as well as on the power generation conditions. Anyway, these is detailedly studied and presented by Mr. Marimuthu, so it's understood by this. So then I will touch upon the cement waste recovery features. How is it we do take care of various challenges or even issues faced so far in the past. So in our boilers, it's indigenous developed. Also, all the things boilers are designed like Mr. Manish was referring to. What are the conditions it required? That means what is the gas outlet temperature? I mean air outlet temperature that required for further processes. Be it is taken care into our consideration. Mostly the boilers are vertical in configurations. So while making the design, like we mentioned, latest developments the design tool. That means without CFD, no boiler is designed. That means we will be doing the CFD analysis for all boilers, so the pH or AQC, because yes, it's very much essential, especially in AQC. The velocity plays a very important role, also the gas distribution, because of the dust is very erosive in nature. So definitely the CFD analysis done. Also the duct, configuration, everything is, done in the CFD analysis. Coming to then we were talking about erosion and baffling and material selection. Yes, it's very much important in AQC boiler, especially when comparing with the pH. Coming to in this, in general, we will be taking care of the design side, whatever the pressure drops. Then coming to whatever the air interest issues, that we very much understand in recovery boilers, in all type of recovery boiler, in specific cement plant, because we'll be handling a large volume of air that's a fans is used. So what are the things? Just I will be explaining when we go to the specific type of boiler. So in principle, we say the improved sealing arrangement at a hammering points. That is we call it as a double sealing arrangement for the hammer, so that that is a one sliding part where there is likely air ingress into the system that is being addressed. And production of pressure parts from erosion by providing erosion protection sleeves. See, there are one is the sleeves, another one is the baffles. In addition, if we come into AQC polar, we'll be providing sacrificing tubes of same material. So the material selection varies based on the temperature what we select. Sometimes T12, that is sometimes T22 also. Whereas the baffles and other things, we straight away go for stainless steel, where it has a very good erosion protection properties. Then coming to also nowadays, this the project timing is very vital. That is, people come with even 9 months, 10 months, and all like this. So definitely the erection time to be reduced at site. So we design the boiler with both modular and semi-modular construction, so that this can be quickly. In one of the projects, we supplied all the AQC modules as like a container like that. Just you stack one over the other. Just finish the seal welding of this casing, then the boiler is ready. This is such an arrangement. This is a preheater boiler. It's a tall boiler with all the accessible platforms and everything is provided with all around. Then a hammering arrangement. Hammering arrangement is always done based on the width of the section. There is a bank, so that the effectiveness is checked whether one side or both sides based on the width of the coils and length of the coil. Based on the length of the coils, whether it's a single hammering or double hammering, it is decided. Then complete seal boxes and also safety, protection covers, everything is provided in this boiler. pH boiler generally single drum water tube natural circulation. Anyway, dual pressure system most of the cases. Then cross flow design it is. Modular design to reduce the construction cost. And construction basically time. Then as I mentioned, specially designed a double seal hammering arrangement to reduce one is noise as well as on the air ingress into the system. Then optimum gas velocity for improved heat transfer surfaces. This is a AQC configuration. In this also single drum water tube boiler, natural circulation, single pressure steam cycle, horizontal pin to tip section, so that the heat transfer areas arranged within a limited space. Then integrated pre-dust collector to remove dust from the gas entry point. This is a one very important equipment in the AQC boiler, so that that dust is collected. I mean, before it's entering the boiler, so that your heat transfer surfaces are well protected. Then the life of the surface is also increased. For this, one is the pre-dust collector and internal design, and also with the modeling or a CFD modeling. Then followed by a sacrificing tubes. Then followed by your pitch arrangement and also support arrangement and baffling at the end of it. That means the end means the plain tube surfaces and bends. How it is protected. It's a very important in the AQC boiler. Again, it's a modular design for quicker erection. Then velocity to prevent the erosion. See, we did a extensive study. Even myself personally visited not only in India, also Chinese. Before we got into this product line, myself personally visited in China and visited. There are 5-6 plants to understand what are the challenges they face and things. Then also here also, even I visited various plants. Then we study what is the customer wants, like what Manish was referring about the damper material selection, as well as although higher gas outlet temperature, how to really control it. Then the air ingress issue, all those then slagging, fouling, how to really make it, how the hammering arrangement to be made, how the impact is studied, and also what is the sequence we need to provide. All these are well understood by our design team, and accordingly it is taken care in the design of it. One is in the process design itself, on the surfaces and other areas, and also arrangement of pictures. Then coming to engineering, also the engineer is very much aware of this. What are the integrity of this? Issues. So we worked with the other consultant or the main consultant who are in the cement industry, cement plants. So we worked with them for improving the overall performance of the boiler also. Coming to this process parameters, even our we have two divisions. One is the boiler as well as the EPC division. EPC, they more focus on the power generation and overall plant construction, whereas the boiler division, we focus on the main core of the boiler. So we both together also we work so that the customer is benefited out of both. That means the boiler as well as in the overall plant performance point of view. It's a typical boiler what we executed for Siroi Cement. To mention, this is a proud moment to mention, we are executing, we backed that. This is the world's largest plant now. Recently, we backed from Siroi Cement to execute cement waste heat recovery boiler. Also, there are customers even we execute 3-4 streams at a time for this cement plant. Just to share what are the plants we executed recent times, starting from the minimum capacity from 4,000 TPD to be gone up to 13,500 TPD plant for this is under execution, whereas the previous ones are already executed and commissioned and are under operations. So we work with most of the customers, and we also with most of the steam conditions also, steam cycle also. Now coming to what we were referring to in this case when we discussed about further, what I can say, heat recovery. One is what Manish was referring to, even the diagram we were showing about the kiln radiation heat. So this is the one area also we were, we have already started, working on this. I know that because myself personally worked on the steel mills like, hoods and other things, also other metallurgical boilers. We know certain areas we need to design with like hood-like construction with a split arrangement. That's what we have been thinking of, but we are to, convert into a project. So we'll be working towards this. So in brief, this is what I wanted to talk about, this boilers and the design features.
Thank you, sir.
Yeah, if you have any questions, I can.
Thank you, sir. Thank you for your very much detailed presentation. Thank you once again. The entire presentation is a really very attractive way, because it is fully carried out your improvements and developments on design aspects as well as the engineering aspects, not about the operation and maintenance side. It is very much useful for all of us. And the seal hammering system arrangements as well as the external hot air generator, these all are also newly explained by you. And detailed explanation given by user. And all the parameters like key parameters like pressure drop as well as the velocity, gas distribution, and the CFD analysis, how you people are taking care during your design and engineering stage, everything is explained by you. Thank you, sir. Now I hand over to Mr. Marimuthu, who can share the question answers if he has received.
Thank you, sir. Thank you to the speakers. Actually, it was a very interesting section. So I have received 3 questions from the participants. So 2 questions to Mr. Ankuraj IJ. So the questions related to the LP system bypassing. So the pH boiler, the temperature input and output is decided based on the raw mill drying. So if you want to have more temperature for raw mill drying, for example, designed for boiler is designed for 200, for 150. If I want the temperature 180 or 200, so can I bypass the LP system? Will it impact my coils or not? So that is the one question.
No, it won't. Also, one more thing, what we can, somebody, even in one of the plant operation, they came with more cooling like this. More cooling in the sense, see, we always design the boiler with a certain fouling, usage factor or fouling factor, right? See, if you allow, the hammering sequence, if we keep changing, right? That means that the frequency of hammering, if you adjust, you can get the temperature adjustment also to an extent. Okay, even we got 10 degree to 15 degree increase when you change the frequency. That means reduce the frequency, increase the frequency. That time gap. Then because of bypassing the gas, it's nothing, because it's a low temperature zone already. The coils are defined.
Okay, okay. So we will not
Also,
face
the
any issue in
circulation
the
is already
coils.
taken care also. Yeah.
Fine, sir. Fine, sir. And another thing is, with the latest technology and with the latest configuration, what is the maximum possible power generation in waste heat recovery system, sir? Mainly in cement plant, in terms of kg MTF clinker. Sorry, in terms of MTM clinker. How maximum kilowatt per MTF clinker, sir?
See,
With
that's
the
what.
latest.
Now, this is again depends. It's not a one parameter, am I right? It is what you already presented. Even we too also notice it varies very wide based on the temperature, the enthalpy. That's the heat input available to this. So also the heat cycle, what you select also. So it's we cannot fix it with one parameter. That's what.
Okay, sir. Sir, nowadays, in India, most of this waste heat recovery plants are operating with the steam Rankine cycle. So, is there any exposure in Kalina and one more cycle? Is there, sir?
See, the other cycles, no. Now all steam cycles only.
Okay, mostly the WHRS are installed with the steam
See,
Rankine cycle.
the next, the other things are likely to be that ORC and other things is likely to come in the different stages.
Okay, fine, sir, fine. Yes, sir. So I think I covered the question and answers. There is no further questions, sir. So over to Durgaram, sir, for concluding remarks, if any.
Okay, thank you, Mr. Marimuthu. Once again, the session was very nicely we have completed, and we have covered all the topics, all the slots within the given time. Thanks to CA executives, and thanks to all the speakers. Without any technical error, also all the slots are covered nicely. I'm happy about those things. Thank you, Mr. Marimuthu, for your all coordination, cooperation with all the speakers and all the things. Thanks to all the management also.
Thank you, sir. Thank you.
Thank you. Thank you, sir. Thank you.
Thank you.